Hello, everyone, and welcome to the IFORS Global Webinar. My name is Mary McGrogan, and I serve as the Secretary on the IFORS Administrative Committee. I'd like to review a few housekeeping rules. Your questions will be answered after all three speakers have completed their presentations. Please use the Q&A button at the bottom of the Zoom screen to direct your questions to the speakers. Please let us know where you're watching from and who your question is directed to, followed by your question. You may use the chat feature at the bottom of the screen to communicate with other attendees. Now, I'd like to turn the webinar over to our IFORS President, Gracia Speranza.
Thank you very much, Mary, for introducing the second IFORS Global Webinar. And it's my pleasure to welcome all of you to this second webinar. We have IFORS has started this series, decided to start this series just recently. And before introducing the webinar, I will give a very short presentation on IFORS. Probably most of you know what IFORS is, but let me just remind the main features of this big organization, which is the mother of all the societies of operations research in the world. In fact, IFORS has 54 member societies, and the number of societies is still growing. IFORS is promoting the development of OR around the world, where it is already developed, but especially where it is less developed, less known as a science. These 54 member societies are organized in 4 regional groupings, and one is, say, covering the societies in Europe, one in North America, the other one in APORS, which is the star of today, Asia, and then we have South America, ALIO. Very briefly, the administrative committee, these are all volunteers offering their expertise and time to work for our community. And you see the organization here of the committee with the vice president, past president, the treasurer, the secretary, Mary, whom you have already met, and the 4 vice presidents who represent the different regional groupings. And you see their names here. And the idea of the global webinars is to have a global webinar organized by one of the VPs. And the idea behind the organization of these webinars is to give sort of light to the different regional groupings and to present to our community some of the best research that is carried out in the different regions of our planet. And of course, given that in these months, we don't have the opportunity to meet in person because all the conferences have been canceled, and likely we will not meet again for a number of months. These global webinars are a tool to get to know each other virtually. This is the best thing we can do, but I think it is very important, and it may create also additional opportunities for cooperation, because we get to know possibly colleagues and research whom we would not have had the opportunity to meet in regular conferences. So today we have this webinar dedicated to APORS. And the first webinar you may have already seen was devoted to ALIO, to the ALIO regional grouping. Today we have APORS, the star of this global webinar. And it's my pleasure to introduce here Francis Miranda, the APORS president, and Suniti, who is our vice president representing APORS within the IFORS Administrative Committee. So Francis will introduce APORS and Suniti will then chair the rest of this webinar. So thank you very much for joining us today, and I'm sure you will enjoy this webinar. Thanks, Francis.
Thank you, Gracia. So good morning, good afternoon, or good evening, everyone, depending on where you are. So yeah, I would like just briefly to talk about APORS. So APORS is a organization and one of the regional groupings under IFORS. So the administrative committee, just very quickly. So myself, and then we have Nizam from Iran, Adiba from Malaysia, and Sudong from China. So I also would like to announce that this year we launched our new website. So this was actually sponsored by IFORS as well. So thank you very much, Gracia and the rest of IFORS on this. So I encourage you to check out this website to see if there are any future events or announcements from IFORS. Next slide, please. Yeah, okay, so on APORS, so APORS is a 35-year-old organization. So currently with 12 countries. So just last week, we concluded the highly successful virtual conference. It was a 3-day conference. It was the first time we did it. And we invited keynote speakers from all the 4 regional groupings, and also presentations from the 12 member countries. So it was a really great event. And our next one is scheduled in 2022 because of the pandemic. We had to move it. So it will be in Cebu, Philippines. So the month will still be finalized. So I would just like to say that I hope I can see all the participants face to face, and I wish that you are all safe.
Okay. Thank you for nice introduction and giving me this opportunity to talk something about our research in this valuable event organized by IFORS and APORS, of course. This is my talk of the today, and let me acknowledge the co-authors, Professor Hamaker and Professor Dembe from Germany, who were my host for the research projects from Humboldt and DAD, and Professor Urmila Pekwaral, who was Humboldt Fellow and is currently professor in my department here, and 5 PhD scholars, Hari, Shiva, Durga, Ram, and Ishwar, and 1 professor from Germany, Mark Yuri. This research is motivated with earthquake, flooding, logistic and locations problems. And moreover, we have many uncertainties, and the traffic demand is high in the large cities, and the infrastructure is very weak. And because of this, we have a lot of problems. Multi type of transportations are running on the road. And with this, we are motivated. And in this talk, I will focus on maximum flow problem and quickest flow problem with contraflow approach and with few applications. First of all, it is very difficult to understand the complex dynamic system. We try to understand it, try to model most of them with using OR techniques, and find optimal planning, and then try to implement them in some cases. The problem has different diversities. If we think about objectives, that may be maximum flow, as I said before, or minimum cost or time, or combining them, giving multi-criteria optimization. There are parameters on the network. Those may be constant or variable, maybe time dependent or flow dependent. and solution may be continuous or discrete. And you can see traveler. The evacuation process may be by the cars, by pedestrians, or planes or ships. There are varieties of mathematical models, starting from analysis or differential equations and optimization. We are working with the network flow. You can see on above, that is discrete model flow, and below is the continuous flow. You can see the motion here, and these solutions can be obtained by solving static flow problems. Here 5s represents static flow, and this is value. So once we have static flow solution, that can be repeated to find dynamic flow solutions over time. So there is one discrete model and again the continuous model. Both solutions can be found like this. And you can see the models here. In this model is to find maximum flow problem over all times. And on the right, with the rate, it is we have to find the minimum time within which we have to evacuate given number of evacuees. And above you can see the flow conservation constants. And this problem can be handled with continuous approach, where the amount of flow that is summed over time is replaced by the rate of flow integrating over the time 0 to theta. And if we want to find continuous solutions via discrete solutions, we have found discrete solutions, and that solution approximates over the time theta to theta plus 1 time interval. And for that time interval, this discrete solution is equals to continuous time, and that is natural transformation. So with this, we can transfer the discrete solution to the continuous ones. Sometimes we have to redirect the flows. For example, here in this network, you can see there is a flow from S to X and X to Y as well. So there is 0 transit time on this arc and 2 transit time on the arc below. Therefore, until this flow departs from S, reaches to X, reaches to Y actually, we are free to use this XY arc, and because there is only one travel time, so we use this path. Afterwards, when this flow that departs from S reaches to Y, the flow that comes through this path has to take this route. Therefore, we have to redirect the flow from X towards Y to directly towards D. So with this, there exists something like negative travel time, and with this we say it is non-standard decomposition, and with this there is an algorithm that solves the problem in polynomial time, or actually efficient time. The main strategy of our work is contrappo. That is very important in evacuation planning. For example, this you can see on the left, it is completely stuck of the traffic halt. On the right, using contrappo, there is smooth. And this was initiated by Shashi Shekhar, mainly giving very efficient heuristics, and started Vardalos and his group analytic, and that we continued with graph theoretic approach later on. And this main idea is add the capacities from both directions and travel time like this. These parameters may be time dependent or flow dependent or constant. See an example here. In this figure, there is a given network, and that is changed to auxiliary network by adding the capacities and respective travel times, as I said before. This means this is two-way network again, and the solution is here on the fourth figure. And the fourth figure solution show that you have from S to Y, that was direction, now it is S to Y. So it is redirected with some algorithm. And then here also, from Y to D, there were two-way directions, and both way directions are merged to give one-way direction from Y to D with some algorithm. And that adds two capacities to have solution through Y to D. The heuristics are very important in this case because these are very large scale problems and have to be implemented in evacuation planning. And this overload degree is calculated with the number of evacuees divided by the bottleneck capacity without contrappo. If it is very small, we are happy because we don't need contrappo, we have an easy solution. If it is average, we need mathematical programming. Mathematical programming works well, but if it is large, then we need heuristics. And there are heuristics. These heuristics improve 40% time by reversing only 30% reversals, but we improved this solution with our result. So there on the left we have network without contraflow. On the right we have network with contraflow, and with this you can see minimum time is here 6 to 7 units or 5 to 6 units with and without contraflow, but the flow is double. You can see from 12 to 24. This problem finding contraflow solution is unfair because here in the below you can see the reversal is done at a time and is fixed, but that may not improve the solution. So we have to reverse the direction of the arcs time to time, and that makes the problem complicated because we have to memory every time, and that takes time, lot of time. Here you can see we have a given network, and in the middle we have a maximum flow solution given by two paths, red and brown, and they can be repeated over time and over and over, temporarily repeated. So that is polynomial time solution. But here on the right we are using this shortest path for the maximum flow solution from the very beginning to the end. And in meanwhile, because if the flow from S starts reaches to the Y, we have to cancel this flow and we have to use another path. Therefore, this solution cannot be temporarily repeated, and this means we use successive shortest path of this, which is pseudo polynomial time algorithm. But these both are same if the network is series parallel. So priority is very important in evacuation planning. If we have a network with priority, terminals are ordered in the priority from X1 to Xk, then we solve this problem like this. You add one super terminal node, and with the super terminal node, if there is connected to the sources, then this arc is deleted and the minimum cost maximum flow problem is solved. And if it is a sink, then the arc from sink to the super source is added and the minimum cost solution problem is solved. Because these two problems are solved polynomial time and we have only finite number of terminals, the whole thing is polynomial. You can see in this example, we improve this solution with the partial contraflow approach because there are solutions on the arc, there are flows on the arcs actually, and that do not need all capacity. For example, you can see from D to X, adding 2 to 4, we have 4 capacities, but we use only 3 capacities. So one capacity is still shaving, and that can be used for the other purpose, that is for logistics or locations. Therefore, we introduce this partial contraflow and we find the better solutions. If we go in the bi-level where there is a leader level and for example maybe government or the customer level, lower level, that may be public, and the upper level wants some network fixed, some part of the network or some part of the paths fixed. For example, from D star to S, some color paths are fixed. With this fixed, the lower level have to find optimal solution, and that optimal solution is adapted by the upper level to use their paths which they already resolved. So this problem is modeled as bi-level optimization, and you can see in the upper level where we have to minimize f with y and phi. Here is not concrete, objective function I have given, but the lower level is we have to minimize the time, and that should fit. So this problem reduces to single level mixed integer nonlinear programming by using KKT conditions. But there are many approaches, many algorithms that has to be applied to solve this single level problem as well. So for the contraflow, if we want to expand the roads capacities or we want to reverse the arcs, we need some cost. So this cost is bounded by B. So we want to improve the flow with this respect in the cost, and this means we have this budgetary constraints feasibility set. So if we add this feasibility set to our previous model, then we can improve the flow with the budgetary constraint. This is quite important problem again. And if we want to improve the flow with rational or integer values, then the static solution is polynomial solvable, but dynamic is pseudo polynomial. But if we want to reverse all the arcs, or we do not want to reverse any of the arcs, then this problem is still unfair, and there is fast polynomial time approximation scheme. Still, the flow, why flow is delayed at intersection is because the flow is coming from upward to going downward, and here coming upward to the downward from the upward. Therefore, there is one W element where the flow is conflicting, the solution is conflicting, and we have to think something about that. So what is way is here we find some solutions using abstract network, abstract flow approach that is avoided. You know, this crossing is avoided. So if we avoid the crossing, we reduce the time and increase the flow. Definitely. Therefore, this problem is solved. This is dynamic flow problem here given model, and this problem can be solved using temporary fitted flow solutions of this maximizing static flow solution, where the weights are given by this t minus time over the path p. But in this model, the drawback is we have to know about the knowledge. We must have the knowledge of the paths before we start the solutions. And still, this abstract flow approach also can be extended to the partial counterflow approach by this number step 2, adding the step 2 in the algorithm, where unused capacities are saved, and that saved arcs can be used for different purposes. Here you can see an example to be motivated with the contraflow, because you can see in the figure that without contraflow we have only this solution, and with contraflow we have a lot of improvement. When the size of the problem increases, the solution gap is bigger. Therefore, for the large size problem, contraflow is very important. We are minimizing the time as well. So minimizing the time, we model this problem as fractional programming problem. You can see we have to minimize t with this fractional programming with these constraints, or we have to solve the parametric mean cost problem with defining alpha equal to this 1 by value of the flow. And this problem can be solved using cost scaling algorithm or cancel and tighten algorithms. And this is easy somehow, because we have to find a static solution and satisfying this constant, and this static flow solution can be repeated temporarily to find the dynamic flow solution. And these, you can see one example to be motivated, that the time reduced from 6.2 without contraflow to 5.37 with contraflow, and you can see the flow rate improvement with it is 480 to 960. So the rate of flow, quickest flow is double. So it is always beneficial. And you can see from the graph also that quickest time increases as the flow problem size increases. And the interesting is, you know, if we have 100,000 cars, we reverse 30% arcs and we get 69% improvement on the solution. And still, in some realistic cases, what may happen that the flow time may be dependent in the flow. That is because, in fact, it is nonlinear thing. So travel time depends on the flow, and that we relax this problem to the info dependent transit times, means the flow interns to the arcs. That rate is same whenever the flow passes to the arcs, but for the different time we have different rate. So that is info dependent, and this info dependent strategy, or again I have another approach here, load dependent transit times. And load dependent transit time is this is travel time depends on the load of the flow that is already in the arc. So with this, both problems can be approximated by 2 plus epsilon approximation algorithms, and that is polynomial time, and that gives only at least, I mean, if t is the time for the info dependent transit time, and it may be twice t for the approximate solution. And the idea to solve this problem is we have to use bow graph. Bow graph is like this. There are different time bows, and this is the fastest, this is the slowest. So we have to shift this fastest solution to the slowest, and therefore the time takes much little more. You can see one example in our tiny example. We use BPR function, and with the BPR function we tested this info dependent transit time, and this is our relation. But in our example, it is only this ratio, 1.04. So we are nearly close to the info dependent transit time is very accurate, I should say. And then with the same scenario, we implement this in the case of Kathmandu Valley, and this you can see the improvement in the quickest flow with the contraflow, and here also you can see info dependent transit times, or say the constant transit time solutions are very close, very near. So if we can find the constant travel times accurately using some techniques, then we can solve the problem info-dependent transit time also approximately. So still we go further with the multi-community approach flows. In the multi-community flow, what we have to do is, there are multi-communities, they are dedicated in S1 and S2, and we have to, or for example in S3, and there are dedicated things D1, D2, D3, they adopt the commodities from S1, S2, S3 respectively. And this problem is quite hard. This is almost from the beginning, it is an hard problem. And we have to, the main problem is we have to share the arcs. So sharing the arcs is difficult, and this problem can be decomposed to the single commodity flow problems. And with solving single commodity flow problem, we use T-length bounded approach, or we use delta condensed solution approach and find approximate solutions for this. So I want to explain this thing here. Here is one arc, and this is has to be shared by all commodities. So this sharing is difficult, and we should think about this sharing. So this sharing was initiated by capacity sharing with resource directive method by in 1972 already. So there are few applications we try to do it, and this application one in flow location problem. So we want to locate the flow, locate the facilities, such that by locating the facilities, our optimality may be lost. We may be reduced to the optimality. If it is maximum may be reduced, or if it is minimum time, that time may be increased. So the thing is, in this graph you can see here it is SY arc. If we put the facility at XY of certain capacity R equal to 1, then we have quickest time 8.5 and we have maximum dynamic flow 3. So the interesting is, you see, quickest time is reduced and maximum time is, is the better one. We have the better maximum time here, and we have better quickest time here if we are very careful. If we put locations in different places, then we are losing some optimality. And we test this with some heuristics. We propose 2 heuristics, and we also model this as integer programming problem. And with this, we have very good solution with the in very quick time. And this is for multi-facility location problem. It is, if it is single facility, the problem is polynomially solved. And finally, we realize that the things, this in the third world, not like in the first world, the problems are different. Scenarios are different because the people don't have many private cars by their own, therefore transit dependent. For example, bus should be there. So we try to implement one algorithm, and that was branch and abound and Tribhuvan. So if the scenario is clear, it is dead. We use branch and abound, and if it is not, then with the different scenarios we use Tribhuvan, and we solved this problem. We evacuated 25,000 above something like people within 29 minutes for the first solution and 36 minutes for the second solution. And the run time was about first 15 minutes, seconds for the first, and about 15 minutes for the second. And still, we realized that we can combine these 2 networks. The first part with the car-based network, and second with the bus-based network, transit network from Y1 to Y1 and Y2 common, because this is source for the second, sink for the first. And with this, we use zero transit time problems and solve this problem polynomially first part, and use heuristic with some dominant rules for the second, and we solve this problem. Or on the other hand, we give priority to the Y1 and Y2 for the first part and find some solutions for the car-based problem, and that indicate to the second part for the bus-based problem, and these are also solved somehow. So thank you very much for your concentration, and have a safe and a pleasant stay.
Thank you, Dhamala sir. Thanks for your very nice research on mathematical algorithm and modeling for evacuation planning and its application in various sectors. Thank you very much, Dhamala sir.
Thank you, madam.
We will have question answer session at the end of the presentation.
Thank you.
Now we have the second presenter, Professor Gokulanand Patel from Birla Institute of Management Technology, India. The topic of his paper is application of DEA tool in analyzing COVID-19. He is a professor in decision science and has long experience of teaching and research, and he has done PhD in Office and Research, MPhil and MS in Applied Mathematics. He is alumni of IIM Ahmedabad. He is working on mathematical programming, performance management, measurement, and MCDM. So he has also more than 100 papers published in both national and international journals of dispute, and he believes in continuous improvement in the courses, in content, as well as in pedagogy, and integrates research and teaching. So that's what all professors do. Now, Patel sir, you also have 20 minutes for your paper presentation. Now, over to you, sir. Thank you.
Thanks. Thanks, Professor. Okay, so this is Gokulanand Patel. Greeting to all respected colleagues from across the globe, from G.N. Patel, Birla Institute of Management Technology, India. I wish I was talking to you in more formal times and not on one where a black swan event, a highly improbable event, COVID-19, which is pushing the world to a terrible new normal. It has fallen to my lot to be the grim chronicler of this disaster, which I am most unhappy to do. On this occasion, please permit me to offer my deepest condolence to all bereaved families on account of the untimely demise of millions of fellow human beings across the world. However, as I have to function to perform, here I am with my topic, analyzing COVID-19 using data envelopment analysis. Okay. So, you see, to start with, I say the world has witnessed several onset and progress of several diseases and epidemics spreading in various regions of the globes over the past many decades. The latest being COVID-19 pandemic, observed first time in December 2019 in Wuhan, China. World Health Organization declared SARS-CoV-2, known as COVID-19, a severe acute respiratory syndrome coronavirus 2 as pandemic on March 11, 2020. WHO further pointed out that COVID-19 was detected in 110 countries at that time, at that March 11. So here, so far it has infected millions of people and killed hundreds of thousands in the world, affecting 215 countries, surpasses 33.8 million cases, with recovery of 25.12 million and death of 1.012 million by today. The highest being USA with 7.41 million affected, 4.65 million recovered, and death of 210,000, closely followed by India and Brazil. Right from the onset, controversy has dogged this pandemic regarding its origin and date. So here, actually, the epidemiology has a long and well-tested history. Such studies are based on focus research, models that describe the essence of pandemic spreading like Ebola, Zika virus, etc. can be used to feed the data with number of parameters, and the obtained values can then be used to make informed decisions. In recent years, research community has focused in management for recovery cases to reduce the death rate. For this interdisciplinary exploration at the interface of statistical and mathematical model, network science and epidemiology, driven by massive amounts of data. In the light of this discussion, the suggestion is to evaluate the two efficiency here for the all countries. The first one, the contagion control efficiency. The second one, the medical treatment efficiency. And based on these two efficiency, we try to categorize all the countries, and you see of countries of countries affected by pandemic COVID-19, considering the country's population density. These are the parameters that I am discussing. Average of 13 international health regulations core capacity scores, IHR-CCS. These are from WHO, and the test facilities, number of corona cases detected, recovered cases, and number of deaths. So these are the variables that are to be considered. So here the two stage, the first one, that what I have written. So for this, we have considered the test to detect corona, and then the population density of the country, and the average IHR-CCS being the input for this model, and the confirmed cases of corona, those are considered as our output. And then in the second stage model, the medical treatment efficiency, the confirmed cases is treated as the input, whereas the death case and the recovered cases as the output. So here I can mention that the recovered cases is the desirable output, whereas death case is undesirable output. And in the inputs for the first one, if you say the population density is beyond the control of the country as present, whereas tests and then average IHR-CCS are under the control of the countries, the decision-making units. So to develop models, I have relied on data envelopment analysis, and for studying this phenomena, I have drawn upon WHO authorized data of 215 countries, and these countries are from all the 5 continents. And now, what a data envelopment analysis is. So just a basic of it. So data envelopment analysis uses linear programming to evaluate the relative efficiency of decision-making units, which produce multiple outputs using multiple inputs. Data may have discretionary and non-discretionary, desirable and undesirable variables. So here are the characteristics of and advantages of DA. This DA does not require the user to prescribe weights to be attached to each input and output, because the performance we measure output to input ratio, and we have multiple outputs and multiple inputs. So the weights, it is not necessary to prescribe by the analyzer himself. It is derived from that data. DA does not require prescribing the functional forms also that are needed as in statistical regression approaches to performance management. Then DA can handle large number of variables and relations. Those are the constraints. And here it makes it easier to deal with complex problems. DA provides number of additional opportunities for use, like opportunities for collaboration between analysts and decision maker, which extend from collaboration in choices of inputs and outputs along with the DMU. And then what if analysis can be, the questions what if analysis can be addressed. Such collaboration extends to benchmarking and what if behaviors. And then what I have said, weights are derived directly from the data. They are chosen in a manner that assigns a best set weights to each unit. The term best is used to mean that the resulting output to input ratio for each unit is maximized relative to all other units when these weights are assigned to the inputs and outputs for every unit. So the best ratio result is general under the following conditions. So here the resulting ratio lie between 0 and 1. The same weights are for the target unit are applied to all units. Consequently, the unit being evaluated cannot choose a better set of weights for its evaluation than this. And then here, for the purpose of securing relative comparisons, a group of countries are used to evaluate each other. And then, as stated earlier, common input and output items for each of these countries are selected as follows. So numerical data are available for each input and output with data assumed to be positive for all DMUs. This reduces the number of countries from 215 to 121 for my analysis. In principle, smaller input and larger output amounts are preferable, but always not for this problem. As there can be comparison between comparable, we group the countries in following ways. Countries having population less than 10 million have been discarded. The leftover 67 countries are further divided into two groups. So the first group, that is the countries having population exceeding 100 million, and this resulted 14 countries. And then the second group, countries having more than 10 million and less than 100 million, resulted 53 countries. And then to start for the model, the notations that we are using, we have M number of inputs, S number of outputs, and N number of DMUs under consideration, where the inputs is denoted by Xij for the ith input of jth DMU, and YRJ is the rth output of the jth DMU. So here, still, if we can represent all these in our matrix notation, that means these actually weights, these weights of the first one, this is the weights of the input actually, inputs weight, V1 to Vm, because we have M number of inputs. Similarly, U, that is U1 to US for the S number of outputs. So these are the weights. And then here for this problem, linear programming problem, this V1 to Vm, U1 to US are the decision variables. So for which the constant ratio model, that is CCR model, constant return to scale, is defined like this one. Okay. So now this efficiency we are defining now, the CCR efficiency is if theta star is equal to 1 and there exists at least one optimal, that is V star and U star, with V star greater than 0 and U star greater than 0. Otherwise, it is CCR inefficient. So we can refer some earlier work like this one. A DA can evaluate the efficiency of a DMU, taking both discretionary and non-discretionary variables into consideration. The non-discretionary variables are beyond the control of management. Even though these variables are uncontrollable, still are important to take into account as inputs so as to estimate the actual measure of efficiency. The formulation of model in case of discretionary and non-discretionary variable can be found in Banker-Murray 1986, Cooper et al. 1997, J. Ruggiero 1998, and then for undesirable outputs can be referred to Seifert and Zhu 2002, Skill 2001, Jahan Sohalu 2005, Liu et al. 2010. So here, first actually we are going to use this input-oriented BCC model, the Banker, Charnes and Cooper model. This is the variable return to scale. This has been the extension of the constant return to scale. And here we minimize theta subject to this. You see x lambda less than equal to theta x naught. That means we require less amount of input. X lambda is less than equal to theta x naught, and this is radially. This is reduced radially, and then we want more output. That is y lambda is greater than equal to y naught. That is x naught and y naught are the inputs and outputs of the DMU under consideration, and the convex constants E lambda is equal to 1 with all lambda greater than equal to 0. This is the general one. But if we are converting this, which can accommodate discretionary and non-discretionary, this we are writing is then for the desirable inputs we have still we want to reduce it. But for that is non-discretionary, discretionary we want less. For non-discretionary we don't want. We cannot. So lambda j, yj still we want more outputs. And then lambda, the convex constants lambda j equal to 1. But these are in the summation notation we write, and all lambda j greater than equal to 0. So this model we are going to use, but this is input oriented. But still I have this one, whenever it is necessary, we can go for the BCC output. This is the output oriented model also. So here in our first page, that means for the contagion control efficiency, number of corona cases, that is, and then is undesirable output, whereas population density is a non-discretionary variable. And in the second phase, death is undesirable output. And then this is output oriented. This is output oriented. Normally, when we maximize the output while using no more inputs, that is the output. That is the BCC model, output oriented. This is the same one. This is the general one. And then with accommodation of, that is the undesirable is bad, and then the desirable is good. So I have written our G and B. This is the model. And then now this countries with 100 million or more population, we have 14 countries. And now this, you see, these are the countries where these 14 countries under consideration over here. This I have taken the data for 9th September 20, and on 26th September 20, the same 14 countries, no change over there. And then here, the countries with 10 million or more and less than 100 million, we have 53 countries here over the world, and same 53 countries also on the 26th September. So here, actually the data set, the phase 1 data set, filtered data set, because you see some data set, we require small inputs and the more outputs. And then you see the testing, whenever the testing is more, if we use it directly, it can affect the efficiency. So we have to take the data reversal. So in few data set, that's why I have written as the filtered data. So this is for the all 14 countries. So you see, this is the contagion control efficiency for the 9th September, 21st September, and 26th September regularly, where you can see the China, as per the data of WHO, the China, USA, over the contagion control efficiency, they are good, even if the Bangladesh, Russia, and Japan. Whereas the contagion control efficiency for India, Indonesia, Brazil, and then your Nigeria, Mexico, Ethiopia, Philippines, Egypt could not succeed to control the COVID-19. And then they could not control the spreading of this one efficiently. And then, but for medical treatment, once the COVID-19 case is detected, so under the medical treatment, most of the countries, they have done well, like China, even if Pakistan, Brazil, Nigeria, Bangladesh, Russia, Mexico. So this is one that I have got it. So medical treatment for this one. Now, based on this, these two efficiency, if we can categorize all those countries, 14 countries, suppose this is for, that is the contagion control efficiency on the x-axis and the medical treatment efficiency on the y-axis. So all these 14 countries can be divided into 4 quadrants. Suppose you see the first quadrant here, the contagion control efficiency is better. That means the countries under this quadrant, they can be benchmarked for your contagion control efficiency. And in third one, the countries falling over that one, they can be benchmarked for the medical treatment efficiency. But we should concern about all those countries which are in the 4th quadrant, which has, that is the contagion control efficiency is less and the medical treatment efficiency is also less. But the second quadrant, if we have taken, this is arbitrarily, I have taken 0.9 and 0.9, thinking that any country having the efficiency more than 0.9, that is acceptable. And then this is 0.9 for this one. So the countries now you can see in the first quadrant only one, that is the USA, whereas in the second quadrant, China, Russia, Japan, Bangladesh, and in third quadrant it is India, Brazil, Nigeria, Egypt, and Pakistan, and the 4th quadrant is the India, Mexico, Ethiopia, and Philippines. Okay, so now for the for the second group, we have 50, this is the part of the data I am showing you now. And then for this one, this is the contagion control efficiency for all these 53 countries, shown here some less amount. But for the medical treatment efficiency, this in the 53 countries, there is much variations in both efficiency. And then this is, if we classify over here, all those into first, second, third, and 4th quadrant, here you see in the first quadrant, even if Rwanda and Belgium, they have the contagion control efficiency better. But in the second quadrant, you see the better quadrant. The second quadrant is the better quadrant, where it is Vietnam, Germany, Thailand, Canada, Australia, Niger, Burundi. And similarly, in the third quadrant here, it's Turkey and up to Guyana. And then there is number of here in the 4th quadrant, we are more concerned. Actually, WHO should be more concerned on these countries lying over the 4th quadrant, and they should be more attentive on this. And now for the reference set, if I am going by this one here, for an inefficient DMU, any country which is not efficient at the particular measure, so we have to find out the benchmark, and this is the one, the benchmarking, and then how much actually we have to reduce the input the required for the discretionary part, not that we are not able to reduce the non-discretionary one. So this is okay. So now you see the reference country scoring for inefficient medical treatment. You can see for the first group I am showing you. This is USA. It is with reference to the medical treatment efficiency. USA can, by the data that I'm seeing, by analyzing those data with those models, USA can refer Russia, whereas Indonesia with China, Mexico with Brazil, Ethiopia with Nigeria and Bangladesh, Philippines with Nigeria and Japan, and Egypt with China. Okay, so this is the target reduction for improvement in percentage for those countries. Okay, so these are the target reduction, means USA should, that is the target for this medical one is that with this 28% like this is the percent. So for this one actually I can say during the process of developing the concepts for this presentation, I had the pleasure of discussing the subject with Professor P.K. Krishnan, who is Professor in Risk and Management and Insurance, BIMTECH, and Professor Pankaj Priya from our institute, BIMTECH. Okay, so this is my last. Thank you for your patient hearing.
Thank you, Patel sir, for your timely presentation. And your research title, this COVID-19, that is the burning issue of current times. So your research is really, really very interesting. Thank you for this. Thank you, and we will meet you in the question and answer session.
Thank you, madam.
Now our third paper presenter is Professor Dongdong Ge from Shanghai University of Finance and Economics from China. His title of the paper is Supply Chain Network Management in Mitigation of COVID-19. He is a professor in Shanghai University of Finance and Economics. He received his doctoral degree in Operation Research from Stanford University in 2009. His main research interests lie in large-scale optimization algorithms and applications and supply chain management in practice. He publishes in journals and conferences such as OR, NOR, NIPS, and many more. He is also the chief scientist and the co-founder of Cardinal Operations. He has consulted for many companies such as Boeing, Google, IBM, IT, and Huawei, many companies. Now, Dongdong, you get 20 minutes for the paper presentation. Thank you. Over to you.
So the topic today is optimization solver. It's development and applications in mitigation of COVID-19. So I just, as Sanity introduced, I work in university, and I also started up a company called Cardinal Operations. So as I said, I changed the topic a little bit because, yeah, I want to talk about recent trends and practice in China, especially during a time of COVID-19. So I work in both academia and the industry. So I think I observed some interesting phenomena here, and I want to share with people in the community. So here's a outline of the talk today. I give a little introduction about the background, why I talk about this problem, and then I give some overview of mass programming solver development, the current situation in China, and talk a little about one solver, COPT solver I'm developing nowadays. And then I give 3 applications, some successful examples during time of COVID-19 in China. So here's the outline. And so as I said, I graduated 11 years ago. Then I started a job as a professor. Later, 5 years ago, I started a company. This might be as I know, might be the only purely OR-oriented company in China. And okay. So so basically when we work on this from data to decision process, it requires a lot of work in data, and finally, at the final stage, you use data to make to formulate a problem and solve a problem. That's a part our people can do. But in order to realize a whole solution, you need a lot of people working on data. So it's not purely about OR. It's a very data-driven AI era now. So we're working with many companies, and some are new customers recently, especially because of COVID-19. So I want to share with you about those examples. First, I talk about those math programming solvers, which I guess everybody knows. There are already many solvers in the world. Many of them are in the United States, and some are in Germany and Russia, and some I know, like Japan has some. And just over the past, 4 years ago, we started to build up our own solver. And 3 years ago, my company and my university, they jointly work together to release a first math programming solver in China called Leaves. Then 2 years ago, Chinese Academy of Science released the second one. Then Alibaba, then our company. Over the past 3 years, there are already 4 math programming solvers released in China, and as I know, some more are coming from like Huawei, from Fudan University, and some other companies. Here I give you some brief introduction about each of them. In 2017, our company, Cardinal Operations, and the Shanghai University of Finance and Economics, they released the first math programming solver in China. This one uses interior port algorithm. It can solve linear programming problem and some nonlinear, like second order cone and SDP problems. And then 1 year later, in 2018, Chinese Academy of Science released the first mixed integer program solver in China. And it claims can solve some hard problems, but you cannot really find too many footprints from the internet. They don't release too much information. And last year, our company released this one called Cardinal Optimizer, which is a very powerful one. Now it's actually, if you check Professor Hans Mittelmann, he has a test web page, very famous one. If you check there, our linear programming module, especially the simplex method, is currently being ranked #1, and it's very fast. And the mixed integer program module is also in good shape. It's already used in many projects in China. We are going to release our barrier solver and our official mixed integer program solver at possibly end of this year. And Copty is actually a very mature one. It can support all the mainstream operating system and all mainstream programming interfaces, and it can also run on the ARM64 platform. And just 2 months ago, Alibaba released also a linear programming solver. Its simplex method module is also very good. It's ranked 2nd on Hans Mittelmann's benchmark website. But it's hard to download. Many people ask for that, but they don't give them yet. We will see. Yeah, here's the benchmark. It's a newest result. It's on September 26th. If you check that, you can see COPT, the solver we developed is a fastest one now, and Alibaba is the 2nd, Groovy is the 3rd now. So very interesting. And here I give a very brief introduction about the COPT team. Actually, it's a global team. You can see our team members are from all over the world, 6 countries in North America, South America, Europe, and China. And here I listed some common modules and the problems, difficulties we encountered when we developed these solvers. I guess I don't have time to talk too much about those things. These are very common problems if you really develop a solver. It's just hard. We spent already 3 years, and what I can see is that it's when we started the project, we know it's hard, but now we still feel it's much harder than we originally expected. And yeah, when we develop a mixed integer program solver, it's even much harder for the code, that's number of codes. The size is like 10 times larger than linear programming module. So it's much harder. I listed some common possible problems when you develop such a solver, and especially when you develop like pre-solve cards, heuristics, all those things, you need to test hundreds or even tens of hundreds of possible techniques to find the most suitable ones for those common problems. So these are very difficult projects, but finally we are on the right track. So I give a few examples to show how these solvers can help people. So first one is about a larger production planning project. This actually is Huawei's project. We worked with Huawei to solve its problem. Huawei is it's a very huge enterprise. So it has like more than 500 workshops, and every day these factories need to handle like more than 50K items, or we call them BL materials, those are raw materials and those parts, and they need to make a schedule, the production schedule, the production plan for the future, like 28 days at a scale per hour. And they also need to make a schedule for the next 10 weeks at a scale days. So that's a very hard problem. Previously, when they handled such problem, because it's too hard to calculate, so they just let each workshop to calculate its own problem. Then they put them together. Then they found that if there are, of course, there are always many conflicts because of over demanding for some same material or same parts. So that requires a lot of meetings, a lot of phone calls, a lot of quarrels. So it's during the COVID-19 time, it's especially hard for them to communicate because it's hard to face to face to do discussion. So they want to develop this automated system. They want one system to handle the whole size problem. So that means you need to put all these factors together to try to solve them using operation research approaches. They use some heuristics with the help of CS people, but those methods don't work well. So now they try OR method. They put all these things together to formulate the problem. Finally, as I said, they get a very huge mixed integer program. It has like 100 million variables, and the number of constraints is at the same magnitude, 100 million. So it's a huge one. So finally, when we finish the formulating, it's impossible to solve. So we solve its linear programming relaxation and use some rounding technique to quickly get a feasible, efficient solution for the final problem. So even we know that even solving this 100 million linear programming problem is very hard. So here is a time sheet we just finished. These are days we use for 3 consecutive weeks. Just past August and September. For 21 days, there are 2 days there are some database error. Other than that, for other days, even either Groovy or COPT worked well. For such problem, because it's still hard for even using linear program. So for such problem, for each day we solve the problem 4 times. Basically, at our first stage, we solve a smaller one, just implement high priority constraints and only solve a 14-day plan problem. So it's a smaller size one. Then we use the output as a fixed known variable. Then go to the second one, enlarge the problem a little bit. By doing that again and again, at a step 4, we can solve a whole size problem. By doing that, the whole problem can be solved basically in 3 hours or 4 hours. 4 hours is extreme the limit for this problem. We need to finish a whole process in 4 hours. So by running this thing for 3 weeks, we found that we can actually solve that one using COPT, and it's actually 10% better than Groovy in running time. So that's one very successful case. By doing that, you can see that the labor or manual intervention time is reduced by 70%, and they also improve order fulfillment rate by 20%. So that's quite successful. The second example I want to talk is about this supply chain network management problem. So in order to do those projects, actually there are lots of companies that are doing similar projects with us recently, including just like what I mentioned, the one I'm going to present, Budweiser, also like Nike, Apple, many global companies, then local branch are working with us for the supply chain problem. Here, let me talk about Budweiser's problem. Budweiser is the largest beer maker in the world. Then during the times of virus, we know that there's very huge violent change of supply chain network and the resources. So when you develop a solution, especially you should contain those emergent changes in business pattern. So your solution must be very quick, agile, and robust. For such things, I think last October or November, we started working with Budweiser. At that time, they talk about the current replenishment plan. It's like they call that as is process. That one involves lots of manual work. Usually, in 2 days ahead, the planner, the people in the headquarters, in Korea, this is a Korea case for Budweiser. In Korea, they have 2 manufacturing centers and 23 regional DC distribution centers. So the people in the headquarters, we call them planners. Those planners, 2 days ahead, they make a forecasting, and then they distribute those information to those warehouses. Those stakeholders from the warehouses communicate with them. Then 1 day ahead, they finish a final confirmation. Then they make a replenishment planning and also arrange trucks. Then at the final day, if there are some very small tail volume adjustment, they need to manage that in the last minute, or some very urgent changes. They need to make a change, make an adjustment in the final day. So this as-is process really depend on the people's experience. They call that expertise experience. So they want to develop some smart tool to automate the whole process. So we worked with them last year. By the end of the year, we finished the development, and you can see here we call that DCP solution. For this solution, it's more like we use a machine learning model to make a prediction. Then after get this demand, at the second stage, we use this, we call it 3-phase replenishment planning. It's actually a mass programming model to solve this problem and give them the business decision suggestion. All these procedures can be simplified just using Excel sheet to do the input and output. So here, this is our mass programming formulation. So we build this objective function and this business constraint. You can see that 2 days ahead, we implement some constraints, and 1 day ahead, we add more constraints, and in the final time, we may add more. So we keep running this model day by day. And this formulation we get, it's a very standard.
Please summarize your paper. The time is going down.
Okay, sure. We get a formulation and we solve it still by COPT. You can see that in 2 minutes we can get a nearly optimal solution. So its performance is quite good. Then here is how do we do the prediction. I will not talk too much about those things, but yeah, it's basically using some inventory management theory and also machine learning thing, and we get this improve the out stock rate and reduce the misallocation unit cost and did a lot of labor saving. Yeah, that's the case 2. And for case 3, I guess I didn't have time to talk about it. It's a power system optimization for a national smart grid project in China, in Sichuan province, and they want to also get an automated system, and this system should be very prompt, flexible, and real-time sensitive. So in Sichuan, there are lots of water power. So they have more than 200 hydro power units and only 70 thermal power units, and they build up this MIP formulation because there are 2 parts. We formulate this and we reduce the numbers. Then we found because there are 2 parts: thermal power subprogram and the hydro power subprogram. So we use this alternating iteration method to divide the problem into 2 parts, and in each iteration of the algorithm, we solve them separately and consequently by deriving the shadow pricing information or gradient information between those subprograms, and we call this improved ADM method. And finally, we found that we can solve all those things in 3 seconds. In the beginning, when we started the project, they need like 300 or even 1,000 seconds to solve the whole problem. So now they can solve a problem just using 3 seconds. And if you use COPT, it can solve a problem in 8 seconds. It's also good. So that's a 3rd project we are doing. So that's my presentation today. Thank you. Yeah. Here's a final page. If you want to take a look at COPT software, you can go to a website to download. Okay, I stop here.